So welcome students. In last class we have already studied about the gas separation using membrane technology. In this class we will continue the gas separation processes and discuss about the flow patterns. Now the flow patterns. So what are the flow patterns? Basically, as I explained you earlier, that in membrane processes we require a large amount of surface area of the membrane. Why? Because the amount of separation depends upon the surface area. Flux multiplied by area gives you the amount of fluid flows from feed side to permeate side. Okay, so that's why we need a large membrane area. So there are different type of flow patterns which may occur inside the membrane modules. So first is the fully mixed flow pattern. It will happen when the you have very small membrane area. If the membrane area is very small, which is the case in the lab scale setup or in the pilot scale setup, then you can assume that the feed which enters in the feed channel is the properties of the feed which enters in the feed channel is constant everywhere. Similarly, the permeates which permeate out from the feed side to permeate side has the constant properties in the permeate channel. Now second type of flow pattern is the cross flow pattern. So in cross flow pattern, the feed and permeates flows in the perpendicular direction to each other. Suppose this is the cross flow pattern. Suppose feed flows in the x direction, then permeates may flow in the y direction or in the z direction, and the different species present in the feed stream will permeate through the membrane in the third direction. So if permeate flow is in the feed channel in x direction and the feed flows in the feed channel in the y direction, then the direction of permeating species inside the membrane will be the z direction. Okay, so why the feed pattern, these flow patterns are important. Suppose in this direction feed flows in this direction, so feed enters in the module from this direction. So here, suppose here concentration is x naught of a given species. So where that species will start to permeates across the membrane in this direction. So the species permeates from the membrane, selectively permeates through the membrane. So the concentration of feed will change in this direction. So you don't have the constant concentration of the feed species which will affect the flux. Similarly, if the permeates flows in this direction, perpendicular direction, then the concentration of permeate from here to in this direction will also change. Okay, so at every point of the membrane you have the different fluxes. Why? Because the operating condition which affects the flux will differs at the differ in the every point of the membrane, at the every point of the membrane. Now third type is the co-current flow direction. Co-current means feed and permeate both flows in the same direction. So in this diagram, feed flows in this direction and permeates flows in this direction. Similarly, there is a counter current flow pattern. In counter current flow patterns, feed flow in this direction and permeates flows in this direction. So we can see that in the mixed flow pattern we have the constant concentration of feed and permeate at the both channels. In the cross flow pattern, feed and permeates flows in the perpendicular direction. In co-current flow pattern, feed and permeates flows in a similar same direction, and in counter current flow patterns, feed and permeate flows in the opposite direction. So among all four patterns, the counter current flow pattern gives the highest efficiency. Why? Because in counter current flow patterns you have the highest driving force across the membrane, because driving force depends upon the concentration. So the concentration difference across the membrane will be higher in the counter current flow patterns. Now we will see the design of the membrane module for the fully mixed flow patterns. We can also design the cross flow, co-current flow and counter flow membrane module. However, the design of that membrane modules are quite complicated, and which requires the computational method to solve. So here we only develop the mathematical model for the mixed flow pattern. So whenever you design a membrane module, the two parameters which you require to know are the stage cut or membrane area of the membrane. So in a given problem, either the stage cut is given and you have to calculate the area of the membrane, or area of the membrane is given and you have to calculate the stage cut. So what is the stage cut? Stage cut is the ratio of amount of material comes out from the permeate side to the amount of materials which enters in the membrane. So here LOL is the amount of material which comes out from the permeate side, and LIL is the amount of material which enters in the membrane. So suppose you want the recovery or the stage cut 70%. So you have to determine how much membrane area is required for 70% recovery. Or suppose it is given that you have a membrane module of membrane area 2 meter square, then you have to calculate what is the stage cut in a given membrane module which has the membrane area of the 2 meter square. Okay, so we have to develop a mathematical model in this way, where if you know the A, then you can calculate the stage cut, or if you know the stage cut, then you have to calculate the membrane area. Now what are the, now suppose we have a binary system which has the two component A and B. The concentration of A in feed side is YIA, and the concentration of B in feed side is YIB, and the concentration of A in permeate side is the product side, which is permeate side, is YOA, and the concentration of B in permeate side is YOB. The concentration of A in the rejection side is XOA, and concentration of B in the rejection side is XOB. Okay, so when you this mixed flow membrane modules are similar to the mixed flow reactor or CSTR. So in CSTR, the concentration inside the reactor is same as a output. So here the output is rejected stream. For this channel, output is rejected stream. So concentration inside this channel should be equal to XOA and XOB for A and B respectively, and concentration in this channel, in permeate channel, output stream is this permeate stream. So concentration of permeate stream in this channel should be equal to YOA and YOB for A and B species respectively. Okay, now here pH is the pressure inside the feed channel, and PL is the pressure inside the permeate channel. LIL is the feed flow rate in the mass feed flow rate, which is given in kg per second. The units of feed flow rate is kg in the kg per second. L is the permeate flow rate, and LOH is the rejected flow rate, or the flow rate in the rejected stream. Now the amount of A species comes out from the permeate side should be equal to, this is the permeate side, should be equal to the overall flow rate multiplied by mass fraction. So mass fraction or mole fraction, if it is given in the LOL given is the mole fraction, then the concentrations are also in the mole fraction, and if LOL in the mass fraction, then concentrations are also in the mass fraction. So amount of A comes out from the permeate side should be equal to LOL multiplied by YOA. So flow rate multiplied by mass fraction or mole fraction equal to the total amount of that species. So amount of A comes out equal to LOL multiplied by YOA. Now the flux of A from the membrane, means flux of A here to here, can be calculated by this equation. I have already derived this equation in the last class. Here J is the flux, the unit of flux is the mass per meter square second or the moles per meter square second. POA is the permeability of component A from the membrane. Delta is the thickness of the membrane. pH is the pressure in the feed side. XOA is the concentration of A in terms of mass fraction of mole fraction in the feed channel. PL is the pressure in the permeate channel. YOA is the concentration of component A in the permeate channel in terms of mass flow rate or moles flow rate, mass fraction or mole fraction. Now here JA, here you can write the LOL minus multiplied by YA, this term, as A multiplied by JA. Why? Because this term gives you the amount of A comes out from the this stream, permeate stream, that should be equal to the area of membrane multiplied by flux, because the unit of flux is mass divided by meter square per second. So when you multiply by flux to area, it will gives you the amount of the flow rate of component A comes out from the permeate side. Okay, now you just substitute the value of JA here in this equation, so you will get this equation. This is the equation first. Similarly, you can write the amount of B comes out from the channel B, which is equal channel comes out from the permeate side, that is equal to LOL multiplied by YOB, because the summation of mole fraction of mass fractions are 1, so you can write YOB as a 1 minus YOA. Now again you can write the LOL multiplied by 1 minus YOA, that is equal to the amount of, this is the amount of B, component B comes out from the permeate channel, or the product comes out in the product, that is equal to A multiplied by JB, and JB can be written by this equation. Here in this equation, here this is the XB, this is the YOB, this is the XOB, this is the YOB. Okay, now we can write this is the equation 2. Now we can write the overall material balance, that is the LIL equal to LOL plus LOH. Here LIL is the flow rate, mass flow rate or mole flow rate of the feed stream. OL is the mass flow rate or moles flow rate of the permeate stream, and LOH is the mass flow rate or mole flow rate of the rejected stream. Now we can write the component balance for component A. So amount of component A enters in the feed from the feed inlet is the LIH multiplied by XIA. The amount of amount of A comes out from the product stream is the LOL multiplied by YOA, and amount of A comes out from the rejected stream is LOH multiplied by XOA. Now we will define the stage cut. Stage cut is equal to the flow rate of the permeate stream, that is LOL, divided by flow rate of the feed stream, that is LIH. Now we define the selectivity or the separation factor, that is alpha equal to POA divided by POB, where POA is the permeability of component A and POB is the permeability of component B. We have also defined a new factor, that is the beta equal to defined as LOL divided by A divided by delta POA. So basically beta is defined to simplify the derivation, and there is no physical significance of beta here. So after defining these three parameters, first we substitute the value of beta in equation 1. So what is the equation 1? So this is the equation 1. So here we just substitute the here we just replace a POA divided by delta to B. So you will get YOA equal to 1 minus beta PH XOA minus PL YOA. So this is the equation 5. Similarly, this is the equation 5. Similarly, you can also write the equation 2. In equation 2, if you replace this term by using the alpha and beta, you will get 1 minus YOA equal to 1 by alpha beta PH 1 minus XOA minus PL 1 minus YOA. Now you have to calculate the value of YOA from this equation, from equation 5, and by using the equation 5 and 6. Why? Because XOA and YOA, these are the, if you again see here, the YOA and XOA and YOB and XOB, these are the output parameters. So it is not the value of these parameters will not given in the equation, in the problem. So you have to eliminate these two terms. So we just eliminate the value of we just determine the value of YOA from these two equations. So this is the derivation. Just we rearrange this equation in terms of YOA. So YOA will become 1 minus beta PH XOA minus, this is the data equation, this is the YOA equation, equation 5. This is the same equation. Now just we rearrange this equation and calculate the value of XOA. So XOA equal to beta YOA plus PL YOA divided by PH. Now we substitute the value of XOA in equation 6. So here we substitute the value of XOA. So once we substitute the value of XOA, you will get this equation. Now we just rearrange this equation in 2 or 3 terms. After 2 or 3 steps, we will get the value of YOA. So YOA equal to alpha minus PH by PL divided by beta alpha minus 1. Now if you check this equation, so YOA equal to PH minus PL by beta alpha minus 1. So alpha is the selectivity. So membrane selectivity is the property of membrane. So it will be given to you ki what is the selectivity of membrane. It is a physical property of the membrane. PH minus PL is the pressure difference across the membrane. So that is the operating condition. When you operate the membrane module, you know that you have to input the pressure at the feed side, and you have to input the pressure at the permeate side. So this is the operating condition. So that will be also given to you. And beta is the multiplication of beta is can be calculated from this formula. Okay, so beta equal to LOL divided by A delta POA. So in this formula also you know the value of LOL, that is the field. In this formula you have to calculate the value of LOL, that is the permeate flow rate, and POA will be given. POA is the basically the permeability of component A, and delta is the thickness of membrane. So beta is basically represent the function of stage cut and the membrane area. Now once you know the value of YOA as well as the value of XOA, so this XOA we have calculated from the here. So we just rearrange this equation. We will get the value of XOA. This is the value of XOA. So So this is the same equation here. Okay, now from equation 4, so what was the equation 4? This is the equation 4. Equation 4 is the, so this is the equation 4. Okay, so it is in the terms of XO and YOA. LIH XIA equal to LOH multiplied by XOA plus LOL multiplied by YOA. This is the material balance for component A. So just substitute the value of YOA and XOA in the just substitute the value of XOA and YOA in the equation 12. So first we substitute the value of XOA here, then we can take the YOA. Here we substitute the value of XOA, then here we take the YOA common in the left hand side, then we substitute the value of YOA. So we will get this equation. So this is our final design equation, equation number 7. This is our final design equation. So in this equation, suppose you want to calculate the, so this equation is in the terms of stage cut phi. So how this phi come? Here you have the HOH minus LOL. So when you divide this two equation by HIH, then you will get the phi term. Okay, and here it is multiplied by LIH. Okay, so this phi is the stage cut and beta is the function of stage cut and membrane area. So suppose you know the value of phi, so just calculate the value of beta from this equation. Other all parameters are, alpha is given to you, it is the selectivity of membrane, pH minus PL will be given to you. This is the pH minus PL is the pressure difference across the membrane, that is the operating condition. pH is the pressure in the feed side, which is also given to you. XIA is the mole fraction of component I in the feed stream, so that you should that is also given to you, how much A is present in the feed stream. So when you know the all this parameter, then just substitute the value of, if you are if the stage cut is known, then you just substitute the all other values in this equation and calculate the value of beta. Once you calculate the value of beta, you can calculate the value of A by using this equation. Okay, and if the stage cut is, if the stage A is known and you want to calculate the value of stage cut, then just calculate the value of beta, then find beta from this equation. Because you know the value of A, you can find the value of beta from this equations. When you find the value from the beta from this equation, just substitute the value here and you can calculate the stage cut. So by using these three equations, so by using equation number 7, then this function you can calculate the, you can design the membrane module for the mixed flow pattern. Okay, similarly we can also develop the mathematical model for cross flow, co-current and counter current flow patterns, but that mathematical models generally consist the partial differential equations, which is difficult to solve on which can be solved by using the computational methods only. So in next class we will study about the per operation process.